The paper I selected to present today is Do Only Look Once, Unified Real-Time Object Detection, or simply known as YOLO. This paper is authored by Joseph Redmon, Santosh Divvala, Girshick, and Ali Farhadi. The content of this presentation is organized as follows. First, I'll give some background information regarding object detection and what led to the invention of YOLO. Then I'll go into the content of the paper, the testing and training phases, loss function, and then the experiments that they have conducted. Finally, the critique, followed by the validity of the paper. So starting with the background, what is object detection? Before we understand what object detection is, we need to know what object classification and localization is. So if we consider object classification, it's basically a single object in an image, and we are trying to classify that object into a certain class. So the output is going to be a class probability. In localization, we are trying to identify an object in the image. So we can use the bounding box or the outline of the object to identify that. In detection, it's for multiple objects, and we combine classification and localization. We are going to predict the class probability for each object that's appearing in the image, and then also the bounding box or the position of that object in the image. So there are basically two types of object detectors, one-stage detectors and two-stage detectors. In one-stage detectors, we are going to input the image. It's going to be divided into grids, and for each grid cell, we are going to get the class probabilities and bounding box regression. So this happens to a single pass to the net. There are no intermediate steps or intermediate algorithms, just a single forward pass, and we are going to get the result. But in two-stage detectors, the image is going to be first divided into regions. So it's going to happen with something like a selective search algorithm, and then each of these regions is going to be classified into classes and also bounding box regression. So there are intermediate steps involved in two-stage detectors. So there can be separate classification steps or various region proposals and various different intermediate steps. So it's more slow compared to one-stage detectors. So if we consider the object detection evolution, earlier there were only traditional ones, and these were not very popular. The most popular one was deep learning. And now deep learning ones are more popular. And if we see in this diagram, it's divided into two. The top ones represent single stage detectors, and the bottom ones represent two-stage detectors. So as you can see, YOLO is the very first single stage object detector. By the time this YOLO was invented, the dominating one was RCNN and its variants like fast RCNN and fast RCNN. So let's see what RCNN does. So it's a two-stage detector, as I mentioned. It's first, if you consider this image, first it's going to extract regions for this image. So it's going to generate around 2000 regions, and it's using selective search to identify this region. And then CNN features are computed for each of these regions, and then it's classified using an SBA. So it's obvious that this is really slow, and it's hard to optimize because each of these phases should be individually optimized. So this is the reason why they invented something like YOLO. So what makes YOLO special? So YOLO frames object detection as a regression problem. We are going to predict real values, bounding box coordinates, and class probabilities. And this is done through a single pass to the network. And also, it processes images in real time at 45 frames per second. They have also introduced a faster version, which runs at 150 FPS. YOLO reasons globally on the entire image. This means it sees the entire image when making predictions. So it's not going to detect background patches as images like in RCL. Also, YOLO learns generalizable representation. This means we can train images on train the model on natural images, and later we can generalize this to something like art. Okay, so the detection phase is common to both training and testing phases. They are going to divide the image into a S by S grid, and each of if the center of a particular object falls onto a grid cell, that grid cell is responsible for detecting an object, detecting that particular object. And also it's going to predict B bounding boxes for grid cell. In the uh, paper they have mentioned B as 2, also the confidence score for each of these boxes, and C class probabilities. And if there's no object in the cell, the confidence score is going to be 0. So let's look at each of these parameters in more details. So consider this image. It's divided into 4 by 4 grid for the sake of simplicity. And each grid cell is going to predict 2 bounding boxes, and there are 20 classes. So if we consider this particular grid cell, let's consider this to be the first bounding box of the grid cell. Notice that the center of the bounding box should always come inside the grid cell. So there are 5 parameters for this bounding box: the midpoint coordinates xy, width, height, and its confidence score. So this confidence score represents how well that bounding box contains an object, and also how well that bounding box represents the ground truth box. Similarly, there can be another bounding box, the second bounding box, since B is 2, with same parameters. And also there are C class probabilities. In this case, there are 20 class probabilities. Notice that even though there are 2 bounding boxes, there's going to be only one set of class probabilities. So the final output is going to be a tensor like this. Since we are divided into a 4 by 4 grid, it's going to be 4 by 4 by 30. So how this 30 comes is there are 2 bounding boxes and each has 5 parameters. So 5 times 2 plus 20 class. So if we consider the network design, it's inspired by GoogleNet. And there are 24 convolutional layers for feature extraction and 2 fully connected layers to predict the bounding box coordinates and class probabilities. So the first 20 convolution layers are pre-trained with 1000 class ImageNet. And then 4 convolution layers and 2 fully connected layers are added to fine-tune this. They have also used reduction layers. The main reason for this is to reduce the feature space from preceding layers. If you consider, they have also considered a smaller version of YOLO, which is fast YOLO. It only contains 9 convolutional neural networks, 9 convolutional layers. Moving on. So if you consider the training test, there are a few key things to consider. As I mentioned, the first 20 layers are pre-trained on ImageNet. Then by adding 4 convolution and 2 fully connected layers, it's converted to detection. They have also increased the resolution of images into 448 by 448 to fine-grained visual information. They are also optimizing some squared error in the model output. The reason for this is, they have mentioned that the reason for this is because it's easy to optimize. But of course, it's possible to replace this. And we have also introduced 2 new parameters, lambda code and lambda norm check. This is because there can be many grid cells without objects. So in that case, the confidence score is going to be 0. So if the majority of the confidence score is 0, the gradient is going to be favored towards those 0 gradient, 0 grid cells. In order to avoid this, they are going to reduce the loss from the confidence score prediction using lambda norm object. It's set to 0.5. And then they are going to increase the loss from bounding box regression. So lambda chord or lambda coordinate is set to 5. They have also used the square root of bounding box width and height. The reason for this is because when using some squared error, it's going to treat small deviation in small boxes and large boxes the same. But in our case, small deviation in small boxes matters the most. Okay, so during training, we can have multiple bounding boxes. but only one bounding box is responsible for predicting this object. So if we consider this particular grid cell, let's take this red color box to be the ground truth box. And the two boxes predicted are this green color one and the blue color one. So as you can see, the green color one best represents the object here in this image. So in order to identify that, we are using intersection of gradient, intersection of union. What it does is, it's going to calculate the area of intersection between the ground truth box and the bounding box, and then divide it by the union of area of the union between the ground truth box and the bounding box. So as you can see, the green box is going to have a higher intersection of union, so it will be selected. Okay, moving on to the loss function. So this is a multi-part loss function, and before I explain it in details part by part, there are a few key terms. So these are called identity function. This is going to have a single value at a given time, either 0 or 1. So this first identity function indicates the jth bounding box predicting cell I is responsible for the prediction. That means there can be many bounding boxes per grid cell. So this is going to be one if if the bounding box is responsible for the prediction, or else it's going to be 0. The next identity function indicates there's no object in the jth bounding box in cell I. And third identity function indicates an object appears in cell I. So as I mentioned, if there's no object in the cell, we need to penalize it. So for that, we need a function to identify if an object appears. So there's also this lambda chord and lambda object, as I explained before. Lambda chord is to increase the loss from bounding box coordinate prediction, and lambda no object is to decrease the loss from confidence prediction. Okay, so let's look at the loss function part by part. So the first two part indicates the loss from bounding box regression. As you can see, the bounding box regression is going to be penalized only if that bounding box is responsible for the detection of this particular object. So if it's not responsible, these parts are going to be 0. And also notice that they are penalized by lambda chord. The loss is increased using lambda chord. This first part is for the xy coordinates, the midpoint, and this second part is for the width and height. So this is done for all the bounding boxes in each grid cell. The third and the fourth parts are the loss from bounding box confidence. So at a given for a given bounding box, only one part of this is going to be used. If that particular bounding box is responsible for prediction, and that means there's going to be an object in that particular grid cell. So then this part is used, and they're using a separate part if there's no object in the grid cell, and this is because we need to penalize it. We need to reduce that loss. So they are using lambda no object for that. And this last part is for the classification loss, and it indicates that there are, as I mentioned, there are each grid cell is going to have a set of classes that it's going to represent. So this is not for each and every bounding box; it's for each and every grid cell, and it's going to calculate the loss for class probabilities, and only if there's an object present. All right, moving on to the inference space. The paper has not well explained the inference space. They have said that it's very similar to training, yes, but there are a few key things like unmax suppression, and the last part is a bit different. So I thought of giving some visual representation of that. So as before, like in training phase, we are going to end up with a tensor like this. So if we consider this grid cell, the first bounding box, it's going to have 5 parameters. Second bounding box is also going to have 5 parameters, and then the rest, that's going to be the classes. So at test time, we need to multiply these class probabilities with the bounding box confidence. So we are going to end up with this 20 by 1 vector. So this represents the class specific confidence score of the bounding box. That means how well this bounding box represents each of these classes. So if we consider this equation, uh, this this is going to represent the probability of each class appearing in the bounding box, and also how well that bounding box locates the particular object. So we do this for the second bounding box as well. Similarly, we continue this for all the grid sets. So if it's a 7 by 7 grid and 2 bounding boxes, we are going to end up with 19 bounding boxes. And then, so here if we consider this dog, there can be multiple bounding boxes predicting this dog. We can say this because this one is the midpoint, on that one is going to predict this. This grid cell might think it's the midpoint and it's going to predict different bounding box. So we need to select the bounding box that best represents this object. So for that, let's imagine the class dog is represented by the first value. Class 0 is this class dog. So here you can see the class specific bounding box values. First, we are going to uh, compare it with the certain threshold and set it to 0 if it's like really small. Then we are going to sort it. So when we sort it, the first value is going to be the bounding box that best describes this object. Then we need to add non-max operations to remove all the other bounding boxes. So what non-max operation does is, so as I mentioned, the first bounding box is going to best represent this dog. And let's see, let's say that the second bounding box, it's something like this. We are going to consider the intersection of units. And if it's greater than 0.5, we are going to set this bounding box to 0. If greater than 0.5 means they might be trying to represent the same object. But imagine there are two dogs nearby. In that case, YOLO struggles because it might remove the second bounding box. And that's some drawback of YOLO. Okay, next we'll calculate this for all the classes. Then we need to find which class the bounding box best represent. For that, we are considering the maximum value. So the index will give us the class that is represent. And if the score is greater than 0, we are going to draw the bounding box, or else we are going to skip. So let's consider like this, and we'll end up with something like this. Okay, limitations of YOLO. So they're only going to predict 2 bounding boxes per grid cell, and there's going to be 1 class per grid cell. This is a major limitation, especially when we are trying to identify a group of objects like a flock of birds, maybe a group of pets. So in those cases, there's a huge limitation in YOLO. And also YOLO struggles to generalize objects in new or unusual aspect ratios. So earlier I said YOLO generalizes well, but what this means is when the ratio of the objects change, let's imagine we are going to classify, we are going to detect beach images. In the beach, there can be people. So let's YOLO. What it's going to learn is it's going to learn aspect ratios, like what's the ratio of this man to the image. Where does this occur? Usually in the bottom of the image. So what kind of abstract characters? There's a head, things like that. So if we change these ratios, if it's very zoomed, you're always going to struggle in those instances. So that's another limitation. And also the loss function. Sum squared error is not the best loss function that we can use here, because it has its own drawbacks, even though it's very easy to optimize. So the experiments. This is something I find very interesting about YOLO, because they have considered many experiments, even something similar to ablation studies. So they have compared it with other real-time systems, VOC 2007 error analysis, combining fast RCNN and YOLO, VOC 2012 results, and then also generalizability test. So comparing with other real-time systems, at that time there were no real-time object detectors. The only ones that are capable of reaching real time was a few GPU implementations of DPM, but as you can see, their mean average precision is really low. FastYOLO was the fastest in the literature at that time, with a FPS of 155. YOLO achieved much higher mean average precision with compared to FastYOLO. And also other ones, they have higher mean average precisions compared to YOLO, but they are not real speed enough. VOC 2007 error analysis, they have compared this with fast RCN. As you can see, YOLO makes many localization errors. This is because it struggles when there are small objects to identify. And localization errors are the most number of errors that it does. But comparing with fast RCN, it does 3 times less background detection. This is something special about YOLO because it sees the whole image. It's not going to detect background touches as image. This is another special thing that they have conducted by combining fast RCN. This is special because rather than just saying it's faster than fast RCN, they have actually combined them to increase the mean average precision. And as you can see, the combination has increased the mean average precision. Also, Pascal VOC 2012 results. As you can see, YOLO doesn't have a very high mean average precision, but it should be noted that it's the only real-time performing object detector in this whole list. And also, fast RCN combined with YOLO is one of the best performers here. In my opinion, I think some cases usability wins over accuracy. So this is something like that. Okay, generalizability. The reason for doing this is because the authors have mentioned that in any object detector, the train and the test sets are derived from the same distribution. So as a result, they are going to fail when they are applied in other domains. So what they have done is they have trained YOLO, RC, and DPM and few others on VOC 2007 and applied on RDET, Picasso and Divvala. So compared to RCN and DPM, YOLO performs really well when it's applied on other domains. This is because even though pixel values are different in artwork, it's going to conserve these ratios. So as I mentioned, ratio is what YOLO learns. So that's why this high average precision is there. So these are few of the results. Moving on to the critique. So these are a few of the strengths that I identified. The extensive array of experiments that they have conducted. And also they have used figures and graphs to well represent the experiments. Mathematical formulations are clearly explained and clearly displayed. And they have also compared it with other models and common benchmarks. So as weaknesses, paper lacks a proper empirical justification for the network design. So they have added reduction layers. They have used pre-trained. So there's no proper reason for doing that. Or why it was pre-trained on something like the dataset that they have mentioned. And also, other thing I noticed was that the inference phase is not discussed adequately. Even though it's possible to implement this just by reading the paper, the inference phase, there are a few additional things to consider. So I think it would have been better if they explained it as well. Concepts like non-mass suppression. So validity of the study. So this was published on IEEE Conference on Computer Vision and Pattern Recognition, which has a very high H5 index of 299. It's also number 1 in engineering and computer science category, and also number 1 in computer vision and pattern recognition category. Also looking at citations of the paper, this has been cited more than 16,000 times. The authors also have a very, most of the authors have higher H indexes. So my opinion regarding the paper is that this is a must read for someone who's interested in computer vision and object detection. Mainly because YOLO is like the foundation for real-time object detection in my opinion. And it is also possible to implement and reproduce the experiments that they have made, even though those benchmarks are not the benchmarks currently. Before is the usual dataset that object detection goes with. Also, YOLO has been extended throughout the past years. There are many improved variations. So I think the authors have done a very huge contribution to the community by inventing something like YOLO.